So this is quiz 2B, or not 2B. It's a bad joke, but I have to do it. There's a line in my contract about having to make that bad joke. The first thing, state two cops and a drunk. Now, there's several statements that are around. There's one in the book for the squeeze theorem, which of course you can use. There went Gracie. But I think one of the better ones is the one kind of on. Let's pull it up. There's one on the pages. So if I come over here to calculus, there's a good one right here. Where it's got, the two conditions of the two conclusions. Now, this is implied by the bottom one. So it's common to not include it's common not to include this condition. It's common to just state the last, the top condition, the top conclusion is kind of implied in the bottom conclusion. You can state it, not state it. They're both the same. But the key for me, and people work differently, but this is how I find when I need to memorize a statement like this, I find it most helpful to do the picture first. So I don't memorize the statement. What I usually do is I memorize the structure. There were two conclusions and there were two conditions and two conclusions. And then I memorize this picture and I construct the statement from the picture that I've memorized. So let's use something similar to this picture, okay, for what's going on. So what I'm going to do is go back to the other one. Okay. So what I'm going to do is I'm going to draw a picture first. And my picture looks like this. So I know that it has to do with limits. There's like an A, and I'm doing the left-handed statement here. It's the same thing for the right-handed statement and the two-handed statement. They're pretty much identical. I have this A in the X space. And I have an L in the Y space. Oops. And then I have a function, f, that's a bit drunk. Okay. And I'll do the left-handed version here. Let me write that in black. So I've got this f, and I have these two functions surrounding it. A top function, or a function that's above, and some kind of bottom function. And these are functions that are easy to deal with. Okay. And then I've got some point after which the function is trapped between them. So I'll call this thing right here left near. Okay. So do you get the sense here that what I'm going to do is I'm going to use the picture to construct my definition. And what I'm going to do is I'm going to memorize the overall structure. So the overall structure is that I have, in this case, you can use the one that's in the notes, which is two conditions, one conclusion. But in this case, I'm going to memorize that there were two conditions and two conclusions. So what I'm going to do is I'm going to write that first. Okay. So now I've got this if condition, okay? So what I'm going to say is, well, top of x is greater than or equal to f of x, is greater than or equal to bot of x. For x left near a. Right, so that was kind of the interpretation of this. I've got, oops. Of course it wants to update. It's Windows. So I've got this, right, I've got this zone here, left near A, where this is true, that top is bigger than F is bigger than bot. And then, and the other condition is that everybody's heading the same place. There's something about the quality. I've got it. People are asking about the quality. I've cranked it up all the way. I don't know what's going on with that. I mean, I can zoom in, make it bigger. Then what happens? Well, then the limit as x goes to a from the left of f of x exists. And again, I don't need this condition because it's implied by the other. By the second, I'm sorry, I don't need this conclusion because it's implied by the other. And f of x to L as x to a minus. Okay. And then what I'll do is so this is the really important stuff. So now I have the really important stuff. I have the if-then structure, I have the conditions, and I have the conclusions arranged. And then I'll come back and add a little preamble. Right, so let top f bot be real functions. Let a in the x space, L in the y space. Okay, so I'm gonna say something like that. Right, and the fact that I'm doing the left-handed version, I would write somewhere as well. But this is not very important. What's really important is the if-then structure, the conditions, and then the conclusion. And of course, only one of the conclusions at this point. And I construct it from the picture. So 1 to 5, how do we feel about that process? So again, the point is that I kind of memorize the picture and construct what I'm doing. Now, if you look at the way the rubric works, so let's ask you, and I want to mention this because this is a common type of question that you get in calculus. Here's the question: how does this type of thing get graded? Okay. So let me move this over in such a way that it doesn't reveal anybody's stuff. Okay. So if I'm looking at the rubric, so if we look at the grader, and the grader's looking at the rubric on Gradescope, okay? And you'll see how this gets graded. It's out of 6. There's kind of a negative. You lose points if you're missing stuff. And then there's some refund points down here. So you've got that this condition is here, right? This person has the condition. That's fine. This person has the condition. That's fine. And all of these other things. You should probably add a rubric item here. Nothing forgot. So does everyone see this? That, you know, this person, that. And then, so having this if-then structure is extremely important. That's that one, -2 if you missed it. This little bit left near, that's -1 if you're missing it. This is extremely important. Obviously here it's bot less than or equal to f less than or equal to top, but you know, that's the same thing in reverse. And this is extremely important. And then right here, I get refunds if I have like a picture. Well, a picture that explains very well that. And I have a good preamble. But it's capped at 6. So let's say that instead I had forgotten this bit here. If I had forgotten that bit there, but I put the general preamble or I put a picture, I would have gotten the point back. I know there's several questions. I got to click on it. So that's kind of how the grading for these works. And I mention it now because it's going to, again, this is going to be something that we're going to see a lot of. All right. So back to what I was working on. Okay. So, are there any questions? All right. Let's see. Okay. So again, if you want to watch the quiz thing, you can do it over Discord. All right. So the limit as x goes to infinity, whatever x. Question 2. Well, the key to this question is to just do yourself some graphs. So this function right here, if you don't know this function by heart, I want you to go print it out on Desmos and draw it and put it over your bed. Okay, when you go to sleep at night, I want this to be the last thing you see until you've got it memorized. Okay, this is the graph of 1 over x, and that you need to have it in your brain for this class. So 1 over x, as I go to the infinities, it goes to 0. And the same things happen here, right? If I raise n to some positive, if I raise x to some positive power on the bottom, it does nothing to what goes on at negative infinity, right? It's either above or below. Either graph is going to be 0. Now, the limit as I go to 0 from the left is negative infinity. And as I go from the right is positive infinity, which means the limit itself does not exist. cosine, as I go to infinity, well, cosine starts up here at 1, goes down, goes up, goes down, goes up, etc., 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 but it oscillates forever. This one's a little trickier. So there are a couple ways to think of this, okay? The easiest way is to graph it and just know what the graph looks like. And if you do that, you know that the graph, that tangent goes up until it gets to pi over 2, and then it just zooms down to negative infinity and comes up. So right here, this is at pi over 2. And it just keeps doing that. So this is at, this right here is pi. This right here is 3 pi over 2. This right here is 2 pi, and it just goes on and on and on and on. Okay. So if I'm doing that, if I'm going to the left to pi over 2, it's going to be that. Negative infinity. Now there's another way to think about this. Okay. And that way is to know what tangent is. So what is tangent? Anyone going to answer me? There are two very good answers for this question. What is tangent? The first is that tangent is sine over cosine. And that way is to just remember, okay, other way. Tangent of theta is sine of theta over cosine. So, as theta goes to pi over 2 from the left, where does sine go? Well, sine, right, the northiness heads to 1. And cosine heads to 0. But it heads to 0 from where? It heads to 0 from the negative direction. So tangent of pi over 2 left is actually 1 over 0 left, which is negative infinity. And I'm going to talk about, this is called the infinitesimal trick. And I am going to talk about that next week. There we go. The other way to do this is to remember is to think about what else tangent is. So tangent here, the way to do this is to remember that tangent is so this right here, if I throw out a unit circle, this is the hypotenuse, which is always 1, the radius. This right here is the length of theta in radians. Okay? And I don't know if you remember this. I don't know if they teach it in pre-calc anymore. But this right here is actually the tangent. So this is the line tangent to the circle at theta. And the tangent function measures the length of this. And by the way, the cotangent function, if you care, Measures the length of that line, of that segment, from not there, from there to there. That's called the cotangent. So that's why this is called the tangent function. It measures the length of the tangent line back to the x-axis. Okay. Now, it happens to be also equal to sine over cosine, but that's not really what it is. What it is this length here. And if you think about this length, okay, if you think about lines, so if I think about this, right, this is a negative slope. The tangent here is negative. This distance right here is negative. And as I move this way, I'm heading more and more. The length here gets longer and longer. I get more and more negative. The length from here to the x-axis gets more and more negative until it goes off to negative infinity. All right. So how do we feel here about number 2? 1 to 5. That's that one. That's that. Sorry, number 2. Yeah. 1 to 5. Okay. I only have 3 people actually watching. Got it. All right. This graph me problem. Let's go over it. What I'm going to do is just what I did last time. I'm going to plot points down and make notes. So when I do this, I'm going to do this in 3 phases, okay? The first phase is notes. Okay? And on this phase, I'm going to have no lines. Except tails, which I can erase. The second thing is connect the dots. And the third thing I'm going to do is I'm going to check. And you kind of have to do all 3 steps. You can't kind of do it all in one go. You kind of have to read, connect, kind of make notes, and do it, piece by piece. So the first thing I'm going to do is I'm going to put negative infinity, infinity on this graph. As I go to negative infinity in the x space, I go to infinity in the y space. That gets a little arrow there. Negative 2 left, 4. All right, negative 2 left, 4. A little tail, just to note which way I'm going. The limit as x goes to 0 of f of x doesn't exist. Okay, what I'm going to do is I'm going to come down here. I'm going to write no limit. The limit as x goes to 1 of f of x equals f of 1. All right, I may have f of 1 defined somewhere else, so I can't really do anything about that yet. I just make a little note. The limit as x goes to 4 from the left is negative infinity. Where was I? Oh yeah, so I did this condition. Now I'm going to do this condition here. So I'm going to draw the limit of 4 left is this right here. I'm going to draw myself a little arrow going down because I'm going down to negative infinity. I got a little asymptote going on here on one side. So I'm going to go ahead and draw that one-sided asymptote kind of as notes. And then the last thing that has to be true is f of 4 equals negative 1. Well, it's not the last thing because there's one more condition. F of 4 equals negative 1. And then I need it to be defined everywhere. So I'm just going to write at the bottom, defined everywhere. Now, I'm done with step 1. So 1 to 5, how do we feel step 1 of graph? So that's step 1. Now step 2 is to kind of connect the dots. All right. So now is when I'm going to draw this thing. All right. So I don't even need to look at these conditions anymore. I need to just look at my graph and where everything is. Well, left to right, this connection's pretty easy. I'm just going to do it. Now, I've got this kind of no limit condition happening here on the bottom. But I don't really have anything else going on. So I just need like no limit here. So, I could draw a squiggly thing to make it look like, sine of 1 over x, but I can actually just do this. Let's give it a jump. And it doesn't matter where the jump is. We'll just give it a jump. Now, I need the limit to equal the y value, but there's no other condition on this section of the graph. The only condition is that wherever I go, I can't have a jump or a hole or anything here. The thing that this says is that wherever I draw the point, I have to have both tails. Now I need to go off to negative infinity. And that's it. I just had this point. But I need it to be defined everywhere. So now I'm just going to go, okay, well, I need it defined everywhere. I'll define it there. And I'll fill in this point. Why not? I didn't have to fill in that point, right? I could have made it defined somewhere else. That's fine too. Either one. Now what I'm going to do, so that's step 2. Step 2 is taking the graph without looking again at the stuff above, taking the graph and just connecting the dots and making a function that satisfies my notes. So I'm not looking at the conditions anymore. I'm looking at my notes about the conditions. So how do we feel about that? 1 to 5. So in one sense, the key to this is not to rush it. In fact, that's the whole key. I don't want to rush it. I want to create a function, and I want to make my notes so that I can deal with things in kind of a local left to right thing. And now I'm going to check it. Now to check it, what I'm going to do is just go down my conditions again. Is it the case that the limit as I go to negative infinity of x, is it the case that I went off to infinity? Yes. Is it the case that as I went to negative 2 from the left, I go to 4? Yes. Is it the case that the limit as x goes to 0 does not exist? Yes, because it's different from the left than it is from the right. Is it the case that the limit as x goes to 1 if f of x equals f of 1? Yes, they're both negative 3. Is it the case that the limit as x goes to 4 from the left is negative infinity? Yes. Is it the case that f of 4 equals negative 1? Yes. Is it the case I'm defined everywhere? Yes. VLT, vertical line test, is that okay? Yes. And I'm done. How do we feel there about step 3? Okay. If you have trouble with this, that's okay. These graphing things are a little difficult. But if you want to work on them, please work on them, because you really need this thing fixed by the time of the test, right? Because you really have to be able to do these well and quickly. I know f is defined everywhere because I have an answer to the question. Is it the case that there's, for any x, is it the case that there's some y associated with that x? And the answer is yes, right? For any x up here, I have an associated y. Okay, it's a good question. Now, so if you're having difficulty with this, there it is. If you head over to the to Canvas, and you go to class notes, and you go here to graphs and functions up here in the week 0 stuff, this activity right here, graphing functions, is actually very good. It's a very good diagnostic utility. And it does help with the teaching first. So if you play with this, it'll help you get the thing straight, because, it's hard, especially if you've been taking classes on the computer your whole life, where like pre-calc is taught at USF, where the computer does the graphing and you kind of just pick it. It's really hard to learn how to create functions and learn the graphing visualizations with that tool, if that's the thing grading you. So if you've never done this on paper before, it's going to be very difficult. And it's something that you're supposed to learn in pre-calc, but you don't because of the computer thing. So if you're having trouble with this, please come see me, print up this activity, and go talk to one of the tutors in the ASC. Remember that we actually have access to ASC tutors. So if you click here, the Tutoring Center, free ASC tutoring, they got virtual study groups as well. But talk to either a tutor or me about graphing functions, because that's something you need to fix up front. Now, there's nothing wrong with it. It's hard. There's nothing wrong with not being able to do it when you got into the course. But there is absolutely something wrong with not being able to do it by the first test. You need to be able to do this by the first test. And I'll be happy to work with you if you're having trouble with it. Okay? Are there any other questions?